Bing, bing, bing.
Doesn't match, you get a 1. If it matches,
Can you
zero.
hear?
So on average, this is, roughly speaking, the fraction of all examples on which you can
ML.
compare. And here we are kind of thinking about this from a classification point of view to check if the class that you output matches the true class or not. But
Guys, we are session 9 out of 20.
But the generalization holds to.
And we are finishing session 9,
Let's
so
stick to classification for now. And we have epsilon hat s of h. This is called the empirical risk.
I want to tell you guys, we
This is
should
the empirical risk or empirical error. This
learn
here
machine
is-
learning. I don't take classes this semester. Maybe it's wrong. By the way, maybe next week, if I feel better, I should go to the class. I feel like, yeah, we can't do
The
lead
difference
code
is that
here. We
this
can
is
learn by
an
ourselves.
process.
But
You're,
there's something
sampling
when
from
there's
mean
you're in an
forever and
environment that everybody
on
wants
average.
to
Whereas
learn the
this is
shit
you have
out of the
finite number
coding,
that's given to you, and what's
and
the
we're
fraction
fine
of
and we're
examples
good
on which
and
we
we'll
make
do it.
an error. Right. All right. Before we go further, there was a question of how adding regularization reduces your variance. So what you can see.
Adding regularization
Let me get back to
reduces
that,
your variance.
in a bit.
That's like a punchline
So-
you can say, right? You're in a meeting, it's a board meeting of a startup or Google, like board meeting. And you say, at the end of the meeting, like they ask, what's your idea? You say, adding regularization can reduce the variance. And everybody is like, wow, dude, how did you know that? Like the manager is happy, gives you promotion. You know, Amir, you can add some regularization to this stupid company that we have. Then I say, yeah, I can do it. I regularize you.
This is called Bayes error.
I minimize your base error. I
This
learned
essentially
all
means
of
if you
this
take
stuff.
best
Just
possible
trust me.
hypothesis. What's the fraction? What's the rate at which you make errors? And that can be non-zero.
How dare he asking me? My rate of making error is 0.
Right? Even if you take the best possible hypothesis ever, and that can still make some mistakes.
No, you're wrong.
And this is also called irreducible error.
Irreducible error. Oh yeah, I remember now. We talked about
For example, if your data
irreducibility, and even in best situation, you may
where for the same
still
things,
have some
different
errors
in two different
because you
examples,
don't have the
then
solution.
no learning algorithm can
Fuck, my leg hurts.
do well in such cases.
It feels better.
That's just one kind of irreducible error. There can be other kinds of irreducible errors as well. And epsilon of H star.
Epsilon of H star. What is H star? Is the best in class H. G is best possible hypothesis. H hat is the learned from the dataset. So G is the best, even the best of the best.
It's called the approximation error.
Between the best in the class. Okay. Yes, actually, that's a good idea. Why? We want G, which is the best possible hypothesis, right? That gives us a clear understanding that how close to the best we are. But I don't think we have it though. And then you say, okay, I have the best in the class, and then I have this. It gives you a feeling of how good you are, right? If you only have the best in the class and learn from the That also gives you the difference, gives you a measure, doesn't it?
So this essentially means what is the price that we are paying for limiting ourselves to some class, right? So it's the error between it's the difference between the best possible error that you can get and the best possible error you can get from H star, right? So this is an attribute of the class. So what's the cost you're paying for restricting yourself to a class? And then you have epsilon of H add minus epsilon of H star, and this you call it the estimation error. The estimation error is,
we have estimation error and we have approximation error. Dude, that's so dumb.
given the data that we got, the M examples that.
How do they name stuff, really? They name to confuse, not to clear.
That we got, and we estimated, using our estimator some H hat. What's the error due to estimation? And this is like approximation.
Mm-hmm.
Right? So the error on G is the Bayes error. The gap between this error and the best in class is the approximation error, and the gap between the best in class and the hypothesis that you end up with is called the estimation error. Right? And it's easy to see that
It's easy to see. Dude, look at me. Shit. Like my. That's so small, it's the size of my cap. Wow, shit. Sorry, I cannot do anything about it. Hopefully, we will get
estimation error
well soon. And
plus approximation error.
I think the only thing I can do is just meeting my protein of the day.
Right? It's pretty easy. If you just add them up, all these cancel out, and you're just left with epsilon of H hat. So it's kind of useful to think about your generalization.
Well,
error.
I agree. The irreducible error is a good name, but approximation error and estimation error, they are very confusing.
Has different components. Some error which you just cannot, reduce it no matter what hypothesis you pick, no matter how much of training data you have. There's no way you can get rid of the irreducible error. And then you make some decisions about that you're going to limit yourself to neural networks or logistic regression or whatever, and thereby you're.
Sorry, last time I looked at my phone. Wasn't. Okay. Alright. Let's focus, guys. Let's
Defining
focus.
a class of all possible models, and that has a cost itself, and that's your approximation error. And then you are working with limited data.
So each error for your
Right.
when you
And with the
find
limited data,
what
you
is
have-
it called? Estimation? No. It is your model, right? We call the H the model. So model has error, and this error is made of three parts. One is even if you have the best of the best estimator, which is the Bayesian, even then it has some errors. Then in the class of functions that you are looking for, because we are doing machine learning or something, we cannot find the best even in that class. So for that we will receive some approximation error, then even because we are not the best in our class, we get estimation error, and all these errors sum up. Even then, we are good, right? We can have 3 errors still. We don't need to be best. We just need to be good enough.
And possibly due to some nuances of your algorithm, you also have an estimation error. We can further see that the estimation error can be broken down into.
This motherfucker is taking me as a puppeteer. He just... Oh, now estimation error can be taken down into 2 bars.
Estimation variance and the estimation bias.
I honestly, I knew it. It's variance and bias.
And
Regularization makes the error less, something like that. I will say it, dude. I will set a meeting with everybody and say, okay,
and what we commonly
my
call as
studies
bias
show
and
that
variance are
estimation,
this we call it
regularization makes the estimation error less.
This is just irreducible.
And I'm not wearing a t-shirt at that time. I'm wearing
Sometimes
suits
you see
and tie.
the bias variance decomposition, and sometimes you see the estimation approximation error decomposition. They're somewhat related, they're not exactly the same. So the bias is basically why is, bias is basically trying to capture why is H at far from G, right? Why is it staying away from G? Why did our hypothesis stay away from the true hypothesis? And that could be because your class is kind of too small, or it could be due to other reasons such as as we'll see, maybe regularization.
I don't touch
Keep
the
you away
phone.
from
I
certain,
don't touch the phone.
hypotheses.
Oh my God,
And the variance is generally due to, it's almost always due to having small data. It could be due to other reasons as well. But these are like 2 different ways of decomposing your error. So now, if you have high bias, how do you fight high bias?
I fight it like I'm fighting death. Bias sounds like high
How
bias.
do you fight high bias? Any guesses?
We will bring the bias low. We add the variance.
Mm-hmm. Yeah, exactly. So one way is to just make your H bigger.
Oh, that's easy.
Right, make your H bigger, and also you can try different algorithms after making your H bigger. And what this generally means is what we saw there was regularization kind of reduces your variance by
Wow.
a small cost in bias. And over here, so let's say
Dude,
your
in
algorithm
2
has
sessions, we will be
some bias.
we will be starting neural networks.
So it has a high bias and some variance, right? And you make H bigger, your class bigger, right? And this generally results in something which reduces your bias but also increases your variance.
Yeah, there is trade-off between variance and bias.
So with this picture, you can also see what's the effect of how does variance come into picture. Now, just by having a bigger class, there is a higher probability that the hypothesis that you estimate can vary a lot.
Hypothesis, they are not models.
If you reduce the space of hypothesis, you may be increasing your bias because you may be
It's
moving away
happening
from
with my
G,
leg
but
too.
you're also effectively reducing your variance, right? So that's the one of the trade-offs that you observe, that any step a step that you take for example, in reducing bias by making it bigger, also makes it possible for your h hat to land at much, at a wider space and increases your variance. And if you take a step to reducing your variance by maybe making your class smaller, you may end up making it smaller by being away from
class
thereby
smaller.
Increase your bias.
Increase your bias.
When you add regularization,
Add regularization.
The question somebody asked before of how does adding regularization decrease the variance? By adding regularization, you're effectively kind of shrinking the class of hypotheses that you have. You start penalizing those hypotheses whose theta is very large, and in a way you're kind of shrinking the class of hypotheses that you have. So if you shrink the class of hypotheses, your variance is kind of reduced because there's much smaller wiggles room for your estimator to place your h hat, and if you shrink it by going away from G, you also introduce bias. That's like the bias variance trade-off. Any questions on this so far?
Bias.
Yes.
Bias.
Yeah, you probably want to think of each of these. You probably want to think of this as a generalized version of this, right? So here we have like fixed theta 1, theta 2, but because you could parameterize them into a few parameters, you can kind of plot it in a metric space. But that's like a more general, like a bag of hypotheses, and But in any case, in both those diagrams, a point here is one hypothesis, a point there is one hypothesis. Here it's parameterized, here it's not parameterized.
Here it's parameterized, here it's not parameterized.
The thing is, so the question is, what if we shrink it towards H star, right? The thing is, we don't know where H star is, right? If we knew it, we didn't even need to learn anything. We could just go straight there, right? So, yeah.
I was never...
With regularization, so the question is, when we add regularization, are we sure that the bias is going up? No, we don't know, and this is a common scenario. What happens, right? When you add regularization, you reduce the variance for sure, but you're very likely going to introduce some bias in that process.
So we add regularization, we reduce the variance,
So
but we are not sure if you're
shrinking your hypothesis space in some way. So you're moving away from 2G, so you're kind of adding a little bit bias.
Bias, we are adding bias. I can see that.
Yeah, so it's
explain nice. I agree.
So
with that.
I would encourage you to kind of after this lecture to think about this a little more slowly. It takes a while to kind of internalize the concept of bias and variance.
Be slow at thinking.
It's not very intuitive, but thinking about it more.
People who think slower are smarter. Let's think.
Right. Any other questions before we move on? So an example of a hypothesis class, right? So an example would be the set of all logistic regression models.
Oh.
Right, and
which is like linear.
When you do gradient descent on your logistic regression class, you're kind of implicitly restricting yourself to set of all possible logistic regression models. That's kind of implicit.
It is the hypothesis? No, it is the Bayesian. No? Is it maybe Bayesian is not a linear?
So the H is the output of
right.
algorithm.
Like in a Gaussian distribution, G will be inside the hypothesis class if we say H is the class of all regularized ones. Right? So if we say the conditional expectation is the best, then it may not be linear. And then our H is the linear family. says like even then we may not find the best linear one. All right.
Right, so you feed an input to your algorithm, and this is not the model. This is the
They
learning
never
algorithm.
talked
Like
about
gradient descent, for example.
Algorithm to
Output of that
find the
is
best
parameters that you learn,
hypothesis.
that converge to.
I don't get it. Maybe it's in the neural network lecture. How we find the good hypothesis. Like we can have some computations and equations to find, for example, a linear function, right? We never had a like algorithmic solution here, or I forgot. Well, what were the kernels about? Kernels gave us like, yeah, we had naive Bayes, we had, okay, so we had some, okay.
Right, so
But it was not like an algorithm, right? What I mean by algorithm is like, okay, do this and add that coefficient by 1. It was like a very theoretical. Maybe it is just
so again,
that.
you probably don't want to think about this as the model that you learn, but this as the training process. And the output of the training process is a model that you learn. And that is a point in the class of hypotheses. Yes, so you fix that the class of learning models. You say I'm only going to learn logistic regression models. Right? For different samples of data that you feed it as
Yeah,
a
for the
set,
beginning I will learn
different.
logistic regression, but later you want to learn more.
Yes, they have to be within the class of hypotheses.
Ah, I see.
All right.
Okay.
So let's move on.
Yeah, let's move on. I feel like we need some new subject. Make it interesting. Yeah, decision trees. Decision trees are good. Ensemble method. I like those. Next session, guys. We will finish these errors and they are all repetitive. Next session, I hope it's very exciting because we are going to talk about decision trees and we are going to decide and make decision when we are sitting on trees, and then we are going to neural networks, which we use the roots of the trees, which is like a network, and it goes all
Empirical risk minimizer. So, the empirical risk minimizer is a learning algorithm. It is one of those kind of boxes that we drew. It is, so in the box that we drew earlier, so the diagram that we drew earlier, based on which we reasoned everything so far, didn't actually tell you what actually happens inside. It could be doing gradient descent. It could just do something else. It could be, some smart programmer who's written a whole bunch of if else and just returns a theta. It could be anything, right? And no matter what,
so we don't know the
algorithm. The bias variance theory still holds. Right? Now we're going to look at a very specific type of learning algorithms called the empirical risk minimizer.
Fuck, I should do something.
So,
the paint changed. I used to sit down and
algorithm, and you
it felt good. Now
star
it got worse. Maybe I should not do the back stretches.
No, H at M is equal to, what is ERM? Empirical risk minimization. It's what we've been doing so far in the course.
I feel like I should not
We
do
try
that.
to find a minimizer in a class of hypotheses that minimizes the average training error.
Hertz.
Right? So for example, this is trying to minimize the training error.
Mm-hmm.
From a classification perspective, this is kind of minimizing the or increasing the training accuracy, which is different from what actually logistic regression did. There we were doing a maximum likelihood.
Actually, I used to have pain here when I
It can be
push.
shown that losses like the logistic loss
Now
can be well
not
approximated
good.
by the ERM.
Like
And,
there is no pain
this theory
here,
should,
which makes me worry
hold
more
on to this.
because the pain is in my leg.
Right? So if we are limiting ourselves to that class of algorithms which work by minimizing the training loss, right? As opposed to something that say returns a constant all the time or does something else. If we limit ourselves to empirical risk minimizers, then we can come up with more theoretical results. For example, uniform convergence, which we're going to look at right now. So we are limiting ourselves to empirical risk minimizers and starting off uniform convergence. So there are two central questions that we are kind of interested in.
Uniform convergence is about convergence in the function space. How is that here? I thought H and this is stuff. Okay, we can have it. And in a finite dimensional space, uniform convergence is just L1 or max convergence, right?
So one question is,
and all of them are equivalent.
If we do empirical risk minimization, that is, if we just reduce the training loss, right? What does that say about the generalization error of that? So that is basically hat of H versus H. So for consider some hypotheses, right? And that gives you some amount of training error, right? What does that say about its generalization error? Like that's one central question we want to consider. And the second one is, what does that say about, if we do empirical risk minimization, that is, if we just reduce the training loss, right? What does that say about the generalization error of that? So that is basically hat of H versus H. So for consider some hypotheses, right? And that gives you some amount of training error, right? What does that say about its generalization error? Like that's one central question we want to consider. And the second one is, how does the generalization error of our learned hypothesis compared to the best possible generalization error in that class? Right? Note we're only talking about H star and not G. Yeah, so H star is the best in class. So these are two central questions that we want to explore. And for this, we're going to use two tools. Right. So one is called the union bound. Right. What's the union bound? If we have k different events, to ek, then these need not be independent. Then the probability of
probability of A.
AK is less than equal to sum of if this looks trivial, it is trivial. It's probably one of the axioms in your undergrad probability class. The probability of any one of these events happening is less than or equal to the sum of the probabilities of each of them happening. Right? And then we have a second tool. It's called the Huffing's inequality. We're only going to state the inequality here. There is a supplemental notes on the website that actually proves the Huffing inequality. You can go through that. But here we are only going to state the result. In fact, throughout the session, we're only going to state results. We're not going to prove it.
Huffing.
So let Z1, Z2,
Z2,
M
GM,
be sampled from some Bernoulli distribution.
Bernoulli
parameter phi.
distribution P.
And let's call phi hat to be
P hat.
the average of them. And Zi, and let there be a gamma greater than 0, which we call it as the margin. So the Huffing inequality basically says probability that the absolute difference between
Absolute difference
estimated
between
phi
estimated
parameter and true phi parameter is greater than some margin can be bounded by
can be bounded by
times the exponential of minus 2 gamma square
That's interesting, to be honest.
m. Right? Not very obvious, but you can show this. What it's basically saying is there is some
So phi hat is the empirical mean of m random variable Bernoulli with the parameter phi, and we know that phi hat will converge to phi almost surely due to law of large number. And Huffing says, okay, this is not machine learning, this is probability theory.
So the Huffing inequality basically
So it
says
says the probability of phi and phi hat being
absolute difference between the estimated phi parameter and the true phi parameter is greater than some margin can be bounded by 2 times the exponential of minus 2 gamma square.
I think it is probably a form of Chebyshev.
Right? Not very obvious, but you can show this. What it's basically saying is there is some parameter between 0 and 1 of a Bernoulli distribution. The fact that it is between 0 and 1 means it's bounded, and that's a key requirement for the Huffing's inequality. And now we take samples from this Bernoulli distribution, and
Interesting.
the estimator for this is basically,
Guys,
and these are just zeros or
probability
ones.
theory is nice.
Each of the Zi is either a 0 or a 1. You sample a 0 or a 1 with probability phi, and the estimator is basically just the averages of your samples, right? And the absolute difference between the estimated value and the true value, the probability that this difference becomes greater than some margin gamma, is bounded by this expression. Right? So there are a lot of things happening here. So probably want to slowly think through this. So this is a margin, right? And this is like basically like the deviation or the error, right? It's the absolute value of how far away your estimated value is from the true. And you would like it to be closer. So you probably want your phi hat and phi to be not more than, I don't know, 0.001, right? So in which case, if the absolute value between the estimated and true parameter is greater than 0.001, if that's the margin that you're interested in, then this the Hufting's inequality proves that if you were to repeat this process over and over and over, the number of times phi hat is going to be farther than 0.001 from the true parameter, is going to be less than this expression, which is a function of m. Right? And that is, you can kind of believe it, because as m increases, this becomes smaller, which means the probability of your estimate deviating more than a certain margin only reduces as you increase m. Right? So this is Hufting's inequality, and we're going to use this. Yeah, questions? Not so. So the question is h star the limit of h hat as m goes to infinity? It is h star in the limit as m goes to infinity if it is a consistent estimator. Right? So we went over the concept of consistency. Right? Given infinite data, will you eventually get to the right answer? And if your estimator is not consistent, then it need not be. So in general, h hat need not converge to h star as you get an infinite amount of data. Right? So now we want to use these tools, tool 1 and tool 2, to answer our the central questions. Any other questions? Yeah. This is a more limited version of Hufting's inequality, and yes, if we limit ourselves to a Bernoulli variable which has some parameter phi, and you take samples from it, and you construct an estimator which is the average of the samples, of the zeros and ones, then this inequality holds. This inequality is called the Hufting's inequality. Yes. So if you're, in general, there is this class of algorithms called maximum likelihood algorithms, maximum likelihood estimators, and a pure maximum likelihood estimator is generally consistent. If you include regularization, then it need not be consistent. Though I'm not very sure about that.
He's not sure.
Yeah, sure.
Gracias. What was that? Bias. What happened? Can I use it here?
Yeah. So basically, for the mic, what he responded was, if you have an algorithm like a neural net, which is non-convex, you may actually not end up with the same result, even if you increase the number of. Though I would probably call the fact, I would probably think of the non-convexity to be part of an estimation bias, because you could, in theory, always find the global minimum of a neural network. It's just that there's some bias in our estimator that we are using gradient descent and we cannot solve it. Okay, so now let's use these two tools.
You
for
use
that,
these two tools,
I'm
fucking
gonna
boring asshole. I don't want to talk to you.
So
Let's use these two tools. Show us something.
over here, we have
Here's those.
hypotheses. Here we have
What happened to my